recording is running. Welcome everybody. Happy Thursday. Kind of doubling down off a lot of stuff we were talking about. Next week is spring break. So although we can't go really out of our houses or do what we normally would have thought we would have for spring break, next week is more of a time to take a break from our learning. So I'll mention this at the end of class today as well. But I want to kind of enable or encourage you to take a break from at least the math class next week. Now, that being said, if you want to get work done, since you're just chilling at home anyways, feel free to do so. But it is a break, so treat it as a break and kind of rest your brain a little bit on my end of things. Again, but if you want to, you're welcome to, but that's my recommendation. So we have, today is our last session of remote learning. It's kind of flown by pretty quick. And it's going to continue to go so at least through May 5th. We'll talk more about it being extended through the end of the school year. Once I get that information, y'all know I'll send out that information to you via email or Google Classroom. But for now, this is our last session until spring break. So what we're going to do today is we're going to go over lesson number 3 in module number 4, which is a fancy way of saying we're going to continue, or not a less fancy way, I guess, of saying we're going to continue our introduction to quadratics. That's kind of a fancier way of referring to it. But first, it looks like there's about 20 of you in here right now. So what I'm going to kind of ask y'all to do is do an informal attendance check by typing in the word here, if you are here right now. So if you are here, please send in the chat box that word here, so that way I can get a vibe of who is here in this session, okay?
You're trying to
take a look at it later on, because I want to try to reward y'all and give y'all credit for being here, since our participation numbers are a little bit lower than I would like them to be. So yes, let me know that you are here, okay? Halfway here, that's better than 0 way here, right on. Okay, cool. So yeah, let's get into our agenda for today and then jump into lesson number 3. Sorry, wrong button. Kind of doubling down on the announcements I made on Tuesday. Just want to start off with kind of reiterating them. Keep in mind that a lot of the unit what we just finished on transformations with our parent functions and our vertical and horizontal shifts, we finished that last Thursday, a week ago. So all of that homework should be being submitted, and a lot of y'all doing a good job on that, but please submit it by tomorrow, and the 2 ed puzzles that related to it. Now, I know I've thrown a lot more ed puzzles onto the Google Classroom since then. Keep in mind that the Google Classroom is basically your guide to what's due and when it's due. It has due dates on all those things, but technically speaking, only 2 of the ed puzzles are due tomorrow. That is the transformations and the parent functions one. Anything that involves that Q word quadratic, not due yet, okay? So 2 new ed puzzles will post it on Tuesday. This is the same slide from Tuesday, so don't stress about that. Remote learning agenda, use the new one. Boom, that's this thing right here. Keep in mind that this is telling us exactly what we're doing and exactly what's expected of us every single day. Notice that we are projected out through May 5th. And if indeed we do kind of get further along the way there, I will extend this obviously to go through the rest of the school year if that becomes the situation. But we've done lesson 29, we've done transformation review, office hours last week. Lesson 2 we did on Tuesday, which takes us to today's date, April 2nd, and we're doing lesson 3. There is an accompanying ed puzzle called Key Features of a Parabola, which posted this morning. And yes, there is an assignment. If you were in the Zoom session on Tuesday or you watched the recorded session, all of this homework in row 5, aka page 417 to 418, the one that I have highlighted in a box right now, we did that on Tuesday, okay? So keep that in mind. But what we're going to do today is progress towards understanding and learning the material to allow us to get 427 and 428 done. That's our goal today, okay? So we're not going to do that homework together in class unless we have time, but that is what we're going to learn today. So use the learning agenda. If you have any questions, please do not hesitate to let me know, as always. And the way that you could let me know, and a lot of you have been doing a good job doing so, is either via email, asking questions here on Zoom, or via this remote learning question, RLQ, remote learning questionnaire, that a lot of you have been filling out. Please continue to do so if and when you get questions, okay? That's pretty much the announcement.
Mr. Benham.
Yeah, what's up, Alyssa?
Okay, so after our Zoom meeting on Tuesday, I sent you an email regarding the homework and assignments, and you never emailed me back.
I will say that I never got an email, so I would go check you're sent. See who you sent to, because I literally sit on this thing and I wait for emails and I try to respond to them. So I know I've gotten a few of your emails previously and I've tried responding to them, to which I've gotten no response from you. So maybe it's just a disconnect on our end, but I specifically don't remember an email. If you did and I missed it, maybe it's in my spam folder. Please just resend it to me, okay?
Okay.
Okay. Sorry about that. If I miss it, I'll get back to you. Anytime I get an email, I'll try to get back to you ASAP. So check in on that, and I'll check on my end as well after the Zoom session.
Mr. Benham,
Yes.
are ed puzzles optional? I forgot it.
Ed puzzles are highly recommended because they're like our classwork. You know, like when we were normally in class, I'd be like, hey, turn to page 400 and do problems 2 through 5, and that would be our classwork. Ed puzzles are basically taking the place of that now. So you will get credit for doing them based on completion, but they're not a homework assignment. They're more like the difference between classwork and homework. Ed puzzles are the classwork. So I would highly recommend doing them for your comprehension and also to get those participation points.
Okay.
All right, great question, Delaney. Any other questions before we jump into today's lesson? Right on. Okay, so if you have any more, never hesitate to let me know. But on that note, let's move in. So again, if you are just now joining or you joined relatively recently, please make sure that you type the word "here" into the chat box so I know that you were present today. All right. So on Tuesday, we introduced these parabolas, these U-shaped things, kind of actually introduced them legitimately, but we saw these a lot in our last unit with our parent function going through the origin, opening upward with a leading coefficient that was positive. But on Tuesday, we started to define these specific things called the axis of symmetry, our vertex, and our specific x-intercepts, which this slide that you see in front of you calls our solution. So we're going to actually learn more about that today. And the way that we're going to do this is through, excuse me, investigating parts of parabolas. We're going to start off on page 391 looking at vocab, and then we're going to do some mixed problems. It looks like approximately 7 or 8 problems of mixed work on pages 420 to 424. Okay, so yes.
Are the are the ed puzzles graded or?
Yeah, so I'm grading the ed puzzles
Okay.
for correctness, but when I eventually enter them into the Infinite Campus gradebook, I will give you participation points. So even if you got like a 20%, like the score I gave back to you was 20%, you will get full credit for trying it. I'm returning the graded answers and the scores to see if you got something right or wrong. And if I just marked 100% on everything, whether it was right or wrong, no one would probably ever go back and look at that because you wouldn't know you got anything wrong. It's a great question, Francis. So yeah, they are graded for participation, but I returned scored ed puzzles for you to see what you got right or wrong. Does that make sense? Right on. Great questions, y'all. All right, so let's jump to page 391. This is in your text. Keep in mind, everybody, that I actually posted all these, the vocab and the homeworks on the Google Classroom, so feel free to join in on that. If you ever need a page or the text, please let me know and I'll get that to you either on the Google Classroom class website or to you individually, okay? All right, page 391, I wanna focus on some specific vocab words here. And the first word I wanna look at is a parabola. And a parabola is effectively just the name for these quadratics. So a parabola is the shape of the curve of a quadratic equation. This is a parabola. And that's an upward or a positive parabola. This is a parabola. And we're only looking at vertical parabolas right now, ones that open upwards or downwards. But as we actually move forward later on in mathematics, we can see that parabolas can be horizontal as well. As a matter of fact, if you have satellite TV, your satellite is a parabola, and it takes the waves from satellites and bounces it to your antenna to get that news feed. So parabolas are highly used in reflections of satellites all around the world. We're looking at vertical ones right now, ones that open upwards and ones that open downwards, positive and negative parabolas. So everything on these vocab words that are highlighted in purple, those are the actual fill in the blank, so to speak. So if you're taking notes at home, you can fill in those blanks. All right, more to come on a quadratic function, that humongous thing right here. We'll talk about that in 1 second. We actually introduced on Tuesday, and if my memory serves, I believe that Andrew gave us a few examples of axis of symmetry in the problems where he was using that as descriptors of a parabola. But long story short is the axis of symmetry is just a line, an imaginary line through the shape that creates a mirror image. the word symmetry means same. And axis is like a line or like a location. So the axis of symmetry on a parabola is like the location of sameness. So if I was going to draw a parabola over here, the axis of symmetry would be where I could cut this parabola in half and have two equal sides. So like the axis of symmetry roughly drawn right now would be that green line. That's my axis of symmetry through my blue parabola. Now, I want to abbreviate the axis of sim there. The axis of symmetry goes through the vertex. So the vertex is the one point that the axis of symmetry always goes through. That's like that center. Boom. Notice that this green line doesn't touch anywhere else on the graph. Not here, not there, not there, not there. None of those places does the symmetry, axis of symmetry go through other than the vertex. Now we're just learning straight vocab and definitions right now. So that way when you hear these words, I'm talking about, as usual, we're not going to have a vocab test on this though, okay? All right, intercepts. We know a lot about y-intercepts. When we were talking about linear equations, we said that the y-intercept was where it ran into the y-axis. But there are also things called x-intercepts, and the x-intercepts are where it hits the x-axis, okay? So intercept is where it runs into something. Thus, we can have x and y intercepts. And by the way, we are going to be using intercepts like to define and solve for quadratics a lot in this unit once we get a little bit further down the road. So it's where it crosses the x or the y axis. Does anyone need any of these words anymore on the screen? The purple highlighted areas, shape, line, crosses, and vertex, those are basically the words that y'all are filling in if you're taking notes right now, by the way. All right, cruising on down. We actually just described what a vertex is. A lot of words going on here. A vertex can be a minimum point, a low point. A vertex could be a high point. It's really dependent upon what they call the coefficient, which just is a fancy way of saying the a value, okay? So like in a positive parabola, our parent function y equals x squared. Notice that the number in front right here is positive, it's positive 1. Our parabola opens upwards. And our vertex, that's the lowest point. We're talking about like range, okay? It's a low point for vertex. Whereas in a negative parabola, and notice that the negative parabola, the only difference between the one in red and the one in green is that there's a negative in front. Well, if it's a negative parabola, it has a negative demeanor, so to speak, to use kind of that cheesy cartoon type of frowning look. And it's just going to be opening downwards. And in which case, our vertex is not the lowest point anymore, but the highest point, like the peak of the mountain. Whoa. Sorry about that. Hit the wrong button. So it's the highest point rather than the lowest point. So vertexes could be min or max values depending upon what we're looking at. Now, the last couple things that I really want to zoom in on today are the actual forms or the formulas of quadratics. We're going to get a lot more familiar with this one as time goes on. And it's f of x or y equals ax squared plus bx plus c, okay? Where a, b, and c are just numbers, like straight up numbers, okay? So this is really kind of crazy looking at first because it's just a combination of a ton of different variables. It looks really cryptic, meaning kind of computer-like or hard to digest. But all of these forms, when we're looking at quadratic equations, are really just numbers, okay? Because we know the word variable means to vary or to change. Thus, the variables a, b, and c could straight up be numbers like 1, 2, and 3. X and y don't change, they're fixed because x's are our inputs, what we plug in a function table, and y is our output, what we get out. And remember, we can always graph anything by using transformations, but specifically by using XY tables, where what we can do to get a graph is plug values in, and then we get out y values to graph ordered pairs. All right. Last thing I want to talk about today specifically in terms of our vocab here on page 392 now, I believe, is the vertex form. And guess what? The vertex form is something that we spent all of last unit talking about. Look at this thing. Okay. where the h and the k actually create a vertex, the lowest or the highest point of a quadratic. So this is a quadratic because it has this power of 2. A tells us how it opens and its stretch. And then the h and the k, these two things, tell us where the vertex is or where its starting point is. All right, again, a little consistency in what they call the vertex form, and it's called the vertex form because it tells us exactly where the vertex is. But I mentioned consistency because it's really building off of everything that's been, where we were able to see a function. Let me get all this off the screen, where we were able to see a function by identifying how it's stretched and how it opens, and the horizontal and vertical stretch, which we now can use to identify what we call the vertex. Boom. So kind of a nice little consistency from where we just left off after about a month or so in transformations. All right, on that note then, let's get into the actual material for today. Lesson 3, page 420, I believe it is. Yep. Okay, cool. So we're on page 420. Number 2 is what we're going to start off with. We have a kind of like from a water fountain, so to speak. And on number 2, they want us to mark the parabola in the water fountain. And here's how we can do that. Ready? I'm basically tracing the water, and sure enough, it looks like a parabola. Sweet. So mark the parabola in the water fountain to show where the height is increasing and decreasing. So we mark the parabola. Now let's show where it's increasing or decreasing. I'm going to use red to show where it's increasing. And increasing means it's going up. And we can describe a parabola much how we read, so from left to right. So this parabola is increasing, going up right here. Increasing. It's going down. We'll mark that in green. It's going down on the opposite side. So as it starts trending downwards, then it goes from increasing to decreasing. And what is this max point called right there? That's our
Vertex.
That's our vertex. Yes, sir. Okay, boom. So this is a downward shaping parabola, increasing on the domain from negative infinity to wherever the vertex is, and decreasing from the vertex to positive infinity. All right. The graph of a quadratic function forms a U shape. You could also say an N shape if it's opening downwards. And it's the name of the U-shaped graph is called a parabola. Looks like parabola. I always pronounce it parabola. Parabola. Parabola sounds like a disease. Okay, next up, number 4 on page 420. We are trying to graph the graph at the right illustrates the location of the x and the y intercepts. Remember, they tell us, boom. Where does this graph run into the x-axis? Oh, at the x-intercepts. Where does this graph run into the y-axis? At the y-intercept. And then sure enough, this is an upward-facing parabola, so it tells us our vertex is actually at our low point, the valley, so to speak, of this U. Okay, so describe what intercepts are in the graph. Well, we kind of just actually mentioned that verbally, but intercepts are where the graph hits the axes. And in this case, the graph is a curve, where the parabola, or the graph, hits the axes. And I'm going to write, I think my English side of my brain is not really working out too well right now. I'm pretty sure that's how you do plural of axes. Yeah, normally right around 12 is where we're going to typically kind of cap this off at. Okay, so again, if you are here and you haven't already wrote in the word here, H-E-R-E here, let me know that you are here for attendance purposes by typing the word here into the chat box. But yeah, we'll be ending right around noon, okay? All right, so our intercepts tell us where it hits the axis. By the way, everyone, as we progress through this unit, which is where we're going to be spending most of the rest of the year on, basically learning all about these quadratics, getting really good at them because they have substantial applications in life, as in Algebra 2. Looking for. Here's the end game. Can we solve for these things? That is our goal. X-intercepts are king. There's a crown for you to remember that they're king, okay? X-intercepts are king. So that's what we're going to be trending towards understanding at a high level throughout our time. But right now, we're running specific axes. Okay. how can we find the intercepts if we have the equation of a parabola? Well, we could use a variety of different tactics. This first one, the factored form, that's going to be super important, very, very important as we continue on, but we don't really know much about that yet, so I want to gloss over it. But the standard form, that's our a, b, and c values, ax squared plus bx plus c, and vertex form, that was last unit, our transformations, okay? So it just so happens that we can use these different forms to allow us to understand specific parts of the parabola. And here's how. Ready? Every x-intercept, let's see if anyone can answer this for me. Every x-intercept has one thing in common. And what I mean by that is this value right here and that value right there, x at -1 and x at 3, they are different x values.
They have the same y.
Yeah, they have the same y value, Francis. You got it, man. What is the y value of every x-intercept?
Pardon?
Close.
Oh, 0.
0, yeah, because if it's on the x-axis, like legitimately, if it's on the x-axis, you're at a height of 0. 0 up, 0 up to be on the x-axis. So every x-intercept has a height of 0. And once we get to the idea of factoring, and we'll learn more about that specifically in lesson 5 and 11, but we can take these factored forms and do what Francis just told us to do, and that's to make the y equal to 0. And what we'll eventually learn, it's kind of a look ahead, but also at the same time, a big kind of aha moment, if you can follow this right now, is that if we're looking for x-intercepts, all we have to do is take the factored forms, the x plus 1 and the x minus 3, equal to 0. So let's just do a quick couple of math problems right now. Let's take x plus 1 and set it equal to 0, where y is equal to 0, because Francis told us that every x-intercept, you're good, Davis, every x-intercept has a height of 0, so I'm literally just making this y equal to 0, and then setting my factors equal to 0. Let's set both my factors, x minus 3 and x plus 1 equal to 0, and let's solve these two equations out real quick. To solve the top one, I subtract 1 from both sides. What's 0 minus 1? -1. Okay. To solve the bottom one, I get rid of subtraction with addition. I add 3 to both sides. What's 0 plus 3? +3. So according to our knowledge, and we'll learn this as the zero product property. Actually, we learned that in the first semester. But effectively, when we use, now that we have an application of what we call the zero product property, it's the following. If you have a multiplication problem, flashback to first semester, a multiplication problem, and it's equal to 0, all you got to do is set your factors equal to 0 and solve. And then take a look at what we got here, y'all. Do we have x-intercepts? No doubt. X equals -1 and x equals +3. So the factored form allows us to solve directly for the x-intercepts using basic algebra, like what we did all in the first semester. We'll learn a dedicated couple lessons on that, like legitimately we're going to spend like 4 days on that kind of stuff, okay? But just kind of a little insight now. Hey, Sarah, thank you so much for sending that out. If you just came here in the chat, you get participation points. I see you, Davis. Is Sutton just with you, Davis, on the same computer?
Rex, what do you have going on behind you, bud?
Yeah, Rex, take whatever you have behind you off, because I have a hunch I know what that is, and I can't see you right now, but. All right, cool. Yeah, I see you, Davis. You're good. Okay, and I have you. All right.
I
Cool.
gather.
So basically, part B is saying the following. We could use a variety of different equations to allow us to see functions. We're actually going to get a little bit more practice with that on numbers 10 through 12. So more to come on that in 1 second. Okay. 5A. Draw an x and a y-axis on the bridge below. Here we go. Let's do this quick. Here's my x-axis in red. Make this a little bit thicker. Boom. And my y-axis I'll do in blue. Cool. Now explain how you chose the origin. I basically chose the origin to be right on my vertex. So that's just kind of a practice in drawing x and y intercepts, axes, excuse me. Now, if I want to draw something that has 2 x-intercepts, here's how I could do it. Ready? 2 x-intercepts means I have to hit the graph on the x-axis twice. So I'm going to cruise my x-axis up a little bit. Why is that solid? Because look at, I have 2 x-intercepts. It hits the x-axis there. in there. All right, one x-intercept. That's like the one I drew on the last page where it only hits the x-axis, the red once. So here we go. One x-intercept says it's only going to hit there once. It hits there right on the origin itself. Now, does anyone think they know how we could draw something with 0 x-intercepts? What do I have to do, just in words?
Below it. I don't fucking know.
Yeah, great call. Below it. So let's make our x-axis below it. Because once the x-axis is below it, is this parabola, which I'm going to draw in purple, is that thing ever going to hit the x-axis? Nah.
No.
So it's not going to have any x-intercepts because it doesn't intercept the x-axis. Those are 3 different types of solutions that we could have as we learn more and more about quadratics. Great call, whoever volunteered that answer. All right, we're making good work. Number 6, use the picture at the right to tell what the axis of symmetry does. So here's our parabola, Mr. Dolphin, or Miss Dolphin, I don't know. Our parabola is the dolphin's body. And this, they claim, is the axis of symmetry right here. I want to abbreviate axis of symmetry as AOS. So the dolphin is the parabola, it's downward, it's negative shaping, its vertex would be at its fin, basically. What does the axis of symmetry do? You want to answer that question? What does that orange line, the axis of symmetry, do? We know symmetry means the same, so what could it possibly do for us?
Those both have the dolphin.
Yeah, good call, Francis. It basically cuts the dolphin in half, so we'll give you a little bit more morbid because we don't want to cut dolphins in half. But it tells us, whoa, I don't know what happened there. It tells us where the middle is, also where the vertex is. It cuts it into 2 equal halves. Nice. Okay, vocab done. Let's get to the actual material for today, which is interpreting graphs. Interpreting meaning taking a graph that's given to us and trying to match it to an equation. Try to hone it and sharpen our skills of understanding these different forms of functions, visual graphs, and mathematical equations, function form. All right, so now let's cruise on down to page 422, and we're going to look at problems 10 and 11 right now. I gave you an equation bank on your text. The equation bank is actually going to be on page 424, I believe, but I copied and pasted it here so that way we could see it in real time together through this screen mirror on our Zoom session. So numbers 10 and 11. Can anyone tell me where they think the vertex is on this beast right here for number 10?
-2, -3.
-3, -3. Super close, Francis. I like that. I like
No,
that.
I said -2, -3.
Oh, my bad. -2, -3. Even better. That's a perfect answer. Francis is right. 2 to the left, 3 down, -2, -3. Now, let's see which equation matches a vertex of -2, -3. Keep in mind, y'all, that every single one of these equations right here are all in vertex form, which is super, super prime, because if we know where the vertex is, all we got to do is find that horizontal shift, the h of -2 and the k of -3, and we know what equation we're working with. So look at this. The h value and the k value of -2, -3? No. 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 Boom. Look at f. Does that have a k value of -3? Yes. And does it have an h value of -2? You might be saying, well, Mr. B, that's a +2, but keep in mind, it always presets at x minus h. So really that x minus h is like the same thing as x minus -2. So do we have a k value of -3? Yeah. Do we have an h value of -2? Yes. So which equation would this one first would be? F. All right. First one done for you. Let's see if we can do number 11 together. Okay, number 11. Anyone other than Francis know where the vertex is on this one? We already did F, by the way, so that one's out. Vertex for number 11.
1,
I
4.
thought 1, 4. Yes, great call, y'all. 1 over to the right, so +1. 1, 2, 3, 4 up. Boom. Vertex 1, 4. Anyone think they know which equation could match 1, 4? Before you, I'm going to eliminate 3 of them, right? I'm going to eliminate 4 of them right off the bat. B isn't going to work. E isn't going to work. H doesn't work, and G is not going to work. Can anyone tell me why I would eliminate B, E, G, and H?
Because they don't have one of the, what is it? I forgot. Never mind.
You're good. And Sarah's already given us the answer, and so is Andrew. The answer to this one is C. Great call, y'all. The answer to this one is C because our H value is +1, cha-ching, X minus H. And our K value is +4, awesome. So that's how they knew that the answer was C. But the reason why E, G, and H is because of this thing in front, what we call the A value. When we have a negative A value, what does that do to a parabola? It opens it, turns it from opening upward, and it reflects it to opening downward. And is this parabola opening downward? Nah. So we could actually rule out B, E, G, and H for all of these positive parabolas because that negative in front means that it would have to be opening. All of these negatives in front mean that our parabola would have to be opening downward, which 10 and 11 we're not doing. But right on, great call on C. That is number 11. Okay, number 12. We know it's not C, we know it's not F, we know it's not B, E, G, and H because they're not negative. Let's do this last one right here, number 12. What's the vertex? Yeah, 1, -2. Great call you up, Sarah. 1, -2. Boom. Bonus question. What is the x-intercept, or what are the x-intercepts? Anyone know those?
Let's see.
Kind of tough on this one because you have to guess.
I think it's -0.5 and
Nice, man. -0.5. And notice that it has a y value of 0. And then, would you say the other one, Francis?
2.5, I'm guessing. Or
Yeah, man. Great
2.2.
call, dude. So Francis
maybe.
made a great recognition there that our x-intercepts are just where it hits the x-axis. Boom. And he had to estimate because they fell between values like such. Yeah, great call you up, Sarah. -2.2 or +2.2, sorry, would be the proper one. But yeah, 2.2 is also good. What about y-intercept? Anyone know what the y-intercept is? Oh yeah, yep, Sarah actually gave it to us on this one. The y-intercept would be where it hits the y-axis, which he wrote as 0, -1. So kind of reiterating or repeating these intercepts here, so that way as we continue to work through quadratics, it all kind of culminates or runs together as to what intercepts are and how we'll be able to see them in form. Okay? Because the 3 forms that we've seen, vertex form, standard form, and factored form, just kind of to reiterate those, the 3 forms that we've seen, like up here, all have different attributes that make solving for quadratics or identifying quadratics really easy. But since we're just being introduced to it today, I'm really just kind of throwing out the basics of this. We'll continue to refine and hone in on those skills as we move forward. Do we think we have an answer for this one? I kind of digressed. I got off topic. We know our vertex is 1, -2. Did anyone think they know which equation works with that?
A.
A, yes, sir. H is 1. Remember, it presets at x minus h. So h is 1, awesome, and k is -2. It has to be A for number 12. Cool. Next up, number 15, cruising on down. We have a few minutes left in class, about 7 minutes left, so we're going to try to get 15 and 17 done. That's kind of our goal today. Well, guess what? What do you notice about number 15 right off the bat? Someone give me a defining characteristic of it. There's a lot of different opportunities. I could define this thing off the top of my head in like 4 different ways right off the bat.
It's going to have a -A.
Yeah, Francis, nice call, man. He knows that it's opening downwards, which means it's going to have a negative A value, which means let's get rid of everything that doesn't. That has a positive A value, +1. B is good because it has a negative in front. That's good. Is C good? No. Why? Because that's positive. We want that to be opening upward. D is no good because it has a positive in front. We don't want that. H and G are good. F is no good. By the way, we already used a lot of those on 10 through 12 anyways. And E is good. And why are B, E, G, and H good? To kind of reiterate that, because this is a negative parabola. So they all have to be equations with negatives in front, reflecting downwards. Great call, Francis. I could also describe this thing in a variety of other ways, like by its vertex, by its x-intercepts, or by its y-intercepts. Those are 4 different ways to describe it. Vertex could be 1, x-intercepts could be a third, y-intercept could be a third. Really all that we care about in this problem is the vertex in the equation. So we've narrowed it down to B, E, G, and H. What's the vertex? I'll give you this one. That looks to me to be 1, 2 to the left, and 1 up. So I know my H is -2 and my K is 1. Which of these equations have an H value of -2 and a K value of +1? Hey, good call, Andrew. B, because look at it opens downward, check. H value is -2, check. K value is +1, 3 for 3, has to be equation B. All right. Again, all we're doing here is we're associating common vocab words, our main things that we're looking for, axis to symmetry, vertex, and x-intercepts. And then we're combining that with our knowledge of how parabolas open from our previous unit, transformations, to throw it all into an equation form. Kind of a little consistency in how the book was set up. Really, really spending a lot of time last unit looking at these different movements of graphs that we call transformations. And then now we get to understand the graphs of this new unit that we're calling quadratics and parabolas. All right, last thing. Last problem for today. Last problem until spring break, that is, even, at least together. What's 17? Anyone got the vertex for me?
-4, 0.
Yeah, -4, 0. And this is an example of something with 1 x-intercept, because our x-intercept and our vertex, our x-intercept and vertex are the same thing. We have 1 root or 1, 0. 1 x-intercept. Great call, AJ. So which one of these graphs has an H and a K, an H of -4 and a K of 0? We only have 3 options left, E, G, and H. So one's kind of tough. It's kind of tricky. Yeah, it's G. It's G. Great call, and great call, Francis, with the actual equation. Nice call, Sarah and Francis and Andrew. The equation is G because it has a H of -4. Remember, it's X minus H, so minus and negative gets us to X plus 4. And a K of 0, it opens downwards, our A value to flashback. The reason why this one was tricky is because E looked a lot familiar, but E would actually be this one. We have a vertex at 0, -4. That would be our y-intercept. So that would be our H of 0 and our K of +4. I think I wrote -4. +4. All right. Hey, y'all did a great job. For those of you that were volunteering, I appreciate the hard work as always and the volunteered answers. Great job. Does anyone have any questions before we kind of wrap it up for today? If you do, either unmute yourself and let me know or type it into the chat box. For those of you who have asked questions previously, Alyssa, again, kind of look back at your email and I'll do the same for mine. And if it got misplaced, I will definitely obviously volunteer.
Yeah, I think I'm gonna email you on my personal email since my school one isn't working.
Okay, sounds good. Sounds good. You
I'll
can also always
email you
comment.
on my personal one.
Okay, yeah, sounds good, Alyssa. I'll look forward to getting your email then. What do I plan on doing for spring break? That's a great question, Andrew. Thank you for asking. I plan on reading, doing a little bit of work, not too much, but then also I built this, I rock climb, so I built this crack machine. It simulates cracks in a rock with a bunch of wood. Not crack as the other thing, but like cracks in a rock, you know, that you can climb it. And I've been spending the last 4 days building this humongous wooden simulated crack in my backyard. So yeah, I'm gonna be practicing a lot on that. So that's what I'll be doing, getting real strong during breaks, trying to stay yeah. What about you, Andrew? Anything? Just
Great
reading.
to hear.
Right on, man.
Cool.
Right on. Just reading sounds like a good way to spend your time. All right then, everybody. I appreciate your hard work as always. I miss seeing you around. I'm keeping my fingers crossed that we get to go back to class and I get to see y'all in person. But if not, at the very least, I'm happy that y'all attended class today. I wish you all a safe and healthy rest of your day and spring break. Get that homework in, get those ed puzzles in, and have a great day. Bye, y'all. I appreciate you as always. And let me know if you have any questions. See ya.